There has been a renewed interest lately in the nuclear bomb, largely due to the release of Christopher Nolan's film Oppenheimer, covering the development and aftermath of the first nuclear device ever detonated. These horrifying devices are capable of unimaginable levels of destruction, yet operate on fairly simple yet remarkable principles of nuclear physics. It may sound like a lot to wrap your head around, but I'm sure by the end of this video, you will get it. When you hear the term weapon of mass destruction or nuclear bomb, a number of terms probably come to mind, like uranium, plutonium, chain reaction, splitting the atom, supercritical or uranium enrichment, and all of these are important aspects to why these weapons work. The first weapons developed were based on the principle of nuclear fission. A heavy element, like uranium or plutonium, was split, releasing an immense amount of energy. But where does all that energy come from? For that, we have to look at the nuclear binding energy. The protons and neutrons that compose all ordinary matter have a free mass of roughly 1 Dalton, or about 1.66 times 10 to the minus 27 kilograms. Protons are slightly lighter than neutrons, but that isn't important for this discussion. What is important is that if you look at a helium atom, which has 2 protons and 2 neutrons, you would expect the overall mass to be about 4.03 Dalton, but it's not. It's actually a little under 1% less than the sum of the individual particles. This missing 1% is called the mass defect, and it is expressed as the binding energy of the nucleus. The binding energy is known for all elements and is plotted here as the binding energy per nucleon. Starting with iron and nickel, which have the highest binding energy, and thus the largest mass defect, and moving towards heavier elements, it continues to slope downwards as the mass defect gets smaller and smaller until we end at uranium and plutonium at the end of the curve. When a heavy nucleus, like uranium, undergoes fission, the new atoms created, called fission products, will be further left on this binding energy curve, and even though the number of nucleons is the same, their overall mass is lower, and the difference is released as a massive blast of energy. And of course, that energy can be calculated using the most famous equation of all time, E equals mc squared, or in this case, delta mc squared. To get an idea of just how much energy this is, the first bomb used in warfare, called Little Boy, which caused the destruction of Hiroshima and ended the lives of tens of thousands and became the colloquial term to refer to the magnitude of large weapons, had a uranium core comprising 64 kilograms of enriched uranium. Of this, only 1 kilogram actually fissioned, and the mass defect generated was 0.7 grams. 0.7 grams, about 1/4 of the mass of a US penny, destroyed a city. Setting off one of these devices isn't as simple as just getting a block of uranium and sticking a fuse in it like conventional explosives. A lot more has to be done right. Each element, or more accurately, each isotope, can be categorized as fissile or not fissile. Fissile simply meaning the atom can be fissioned, or split apart, and it can sustain a nuclear chain reaction. It will just keep on going once it starts. An isotope of an element is simply variations in the number of neutrons in a nucleus. A given element always has the same number of protons, but isotopes of that element can have fewer or more neutrons. For example, hydrogen is usually composed of 1 proton, an electron, and no neutrons. But deuterium is an isotope of hydrogen that has 1 proton and 1 neutron, and this is the hydrogen component in heavy water. Chemically, it behaves the same, but has different properties in nuclear physics. The key isotopes of uranium are uranium-238 and uranium-235. Uranium-238, consisting of 92 protons and 146 neutrons, is the primary isotope of uranium found in nature, and it is not fissile. Fission works by bombarding a nucleus with a neutron. When absorbed, they impart the necessary energy and conditions to force the nucleus to break apart into the fission products. In order for this to work, you need a material that not only breaks apart when absorbing a neutron, but is also a large enough target to easily absorb neutrons, and when it breaks apart, it must release on average more neutrons than it took to split in the first place to create the exponential chain reaction. The likelihood to absorb a neutron is measured as an area in the unit of barns. I'm not going to do the conversion from square meters here, but it is very small. Hydrogen has a neutron cross-section of 0.332 barns. Uranium-238 is 2.71. but uranium-235 is a massive 582. And plutonium-239, the other common nuclear fission fuel, has a cross-section of 746 barns. Uranium-235 and plutonium-239 also release enough neutrons to sustain the chain reaction and are thus the fuels used in bombs as well as nuclear power plants. Uranium-235 is found in trace amounts in natural uranium, which must be enriched using a variety of processes to separate out the uranium-238 from the uranium-235. With a mass difference of only 3 neutrons in the same chemical properties, it makes it incredibly expensive and impractical to produce in large quantities, and thus wasn't used too often. A sufficient amount of these fissile materials needs to be combined to form a critical mass, the minimum amount of mass needed to start the reaction at a given pressure and temperature. Once at critical mass, the device will go off, so it was important to make sure that the critical mass is reached only at the time of detonation. This led to the first weapons developed, and they came in 2 types, the gun type and the implosion type. The gun type used uranium as its fuel and was the design principle of Little Boy. Quite simply, the uranium core was split into 2 pieces, a cylindrical bullet and a circular rod. The bullet was fired into the rod at the time of detonation, assembling the critical mass and thus the explosion. The reaction is typically over in 1 microsecond, which is under a millionth of a second, because it doesn't take long for the immense amount of energy to expand and break up the critical mass, stopping the reaction. Plutonium weapons, using the implosion design, quickly became preferred because of just how difficult it was to produce the uranium-235 needed to fuel it. Plutonium couldn't be used in this gun type of weapon because the assembly of the critical mass was too slow to ensure efficient use of the plutonium. Plutonium was significantly easier to mass produce once nuclear reactors were built, because you may notice plutonium-239 is only 1 nucleon away from uranium-238. And by essentially placing a bunch of uranium into a nuclear reactor, neutrons emitted from the reactor are absorbed into the uranium-238, becoming uranium-239, and then after a few radioactive decays, it naturally ends up as plutonium-239. This is referred to as reactor-bred plutonium. In the implosion type, a single core of plutonium is used, and at standard temperature and pressure, it's not at a critical mass in its resting state. At the time of detonation, a series of explosives surrounding the plutonium core are detonated in unison, forming a uniform shock wave that compresses the plutonium core from all angles simultaneously, doubling its density, and thus reaching a critical mass, and nanoseconds later, a nuclear blast occurs. To ensure maximum efficiency, uranium tampers surround the critical mass to keep it contained as long as possible and reflect neutrons back into the core to fission as much material as possible in the very brief reaction period. This is the type of device used in the Trinity nuclear test and eventually Fat Man, which was dropped on Nagasaki and became the preferred device for all weapons going forward. These early nuclear devices had explosive yields on the order of 20 kilotons of TNT, but you may have heard how modern thermonuclear bombs have yields in the megaton range, or 1,000 times the power of the bombs dropped on Hiroshima and Nagasaki. In addition to more efficient designs of weapons causing higher fission yields, the big principle that led to this order of magnitude increase in power is from the fusion of heavy hydrogen. Remember the binding energy curve and how much energy we got from splitting uranium? Well, although splitting heavy atoms releases energy, you can also get energy release from fusing lighter atoms. The amount of energy released from fusing hydrogen into helium is astounding, and is the reaction that powers the sun. Thermonuclear bombs are 2-stage fission-fusion devices that use an implosion device to create a necessary energy to begin the fusion of hydrogen, and thus these bombs are commonly known as hydrogen bombs or H-bombs. I hope you found this insightful, and I would be happy to answer any questions you might have in the comments below. Thank you so much for watching.